So finally, we need to work out what the uncertainty, the error, in our final value for G is. Now remember, we worked out the value for G here based only on the gradient. G equaled pi squared over m squared. So if we apply the same idea of working out uncertainties to that, G equaled pi squared over m squared. Pi squared doesn't have an uncertainty. Just make sure that you use enough decimal places for pi that it doesn't cause a rounding error. But you're probably not likely to be working in more than 3 or 4 decimal places, so 3.14 squared, probably fine. Better still, just use the button on your calculator and you've got plenty to go at. So G depends on m. So if we want to apply the uncertainty equation, delta G over G equals delta M over M. But of course it's squared, so it is involved twice. So what we'd normally do is say, well, that would be delta M over M again. But of course that's just 2 times delta M over M, which gives us a relatively easy equation. Therefore, the uncertainty in G can be rearranged and we just have to make sure we understand what each of these things are. So, G is your calculated value for G. So, i.e. what you worked out up here when you did the gradient of the graph and you worked out G from that. That's your value for G. M is the original gradient. So again, the one that you worked out G from. Delta M is going to take a little bit more thought. This is from the max-min gradient. So I'll just quickly remind you how to go about finding the max-min gradient and therefore delta M. So if you've got your values of t and root x plotted on a graph, and this gives you your original line of best fit. That line gives you M, your original gradient. If you look at the scatter of the points, and if you've got error bars, this becomes even easier to do. If you've not, you've got to judge it off the scatter as best as you can. You would draw a second line of best fit. Whatever you think you can get away with as being the most extreme line of best fit, while still being a line of best fit. Just with this random sketch I've got, I think it's actually probably about there. Or maybe that's a bit too extreme. Yeah, that's not brilliant, but it'll do for the sake of an example. So this is going to give me a much lower gradient. So this is going to be my minimum. And it's going to give me M min. Now I could have gone the other way and got M max. Doesn't matter. You just need an extreme line that's going to give you an extreme gradient. Delta M would be the difference between the gradients. Easy as that. So it doesn't matter if you used a maximum. Obviously, you might, if you did it one way around, you might get a negative number. It doesn't matter. It's the difference. The positive or negative doesn't matter. This is giving you delta G. Now remember, when you quote your final answer, you have to give it in the right format. So G equals, for example, let's say you got 9.5. And let's say for delta G, you got 0.4. You could write it like that. So this is your value for G, and this is your value for delta G. Whenever you quote G, every time you quote G in your results, in your abstract, in your discussion, even in your conclusion, that's what it should look like. Okay, so whatever your values for G are and whatever your uncertainty was. The units could be meters per second squared. Don't forget, they could also be newtons per kilogram. Nobody's going to argue they are equivalent. And that's it. That's all of the processing you need to be able to do.